All right, ever really thought about this? A firework explodes, boom, it's over in a flash of light. But then you've got an old iron gate, and it takes, well, decades to rust. They're both just chemical reactions, right? So why the massive difference in speed? That's what we're digging into today. The secrets behind reaction speed, or what chemists call chemical kinetics. I mean, really, let that sink in. One is this explosive, super fast event, and the other is, well, it's the definition of slow, a quiet process happening over your entire lifetime. So, what's the deal? What's the hidden control knob that nature is twisting to make one happen instantly and the other take forever? That question right there is the heart of what we're going to unpack. So, here's the game plan. First, we'll cover the basic rules of reaction. Then we'll dive into the single biggest factor, the energy gatekeeper. After that, we're going to see how we can actually watch these reactions happen. And finally, we'll check out the different tools chemists use to do it. All right, section 1, the rules of reaction. So before any chemistry can even start, there are some, let's call them non-negotiable ground rules that have to be followed. And it all starts with something called collision theory. And honestly, it's exactly what it sounds like. For two molecules to react, they have to actually collide. They have to physically bump into each other. You know, no collision, no reaction. It's rule number 1. And it makes sense, right? The more you can get them to collide, the faster your reaction should be. But, and this is a huge but, just bumping into each other isn't enough, not even close. In fact, the vast majority of collisions do absolutely nothing. For a collision to be effective, for it to actually work, 3 things have to happen all at once. First, they have to collide. Second, they need to hit each other with the perfect orientation, kind of like 2 puzzle pieces that only fit one way. And third, and this is the big one, they have to smash together with enough energy. And that last point, energy? Well, that brings us to the biggest hurdle of all. This is the real gatekeeper when it comes to reaction speed. This minimum energy is called the activation energy, or EA, and the best way to picture it is to think of a big hill. Your starting chemicals, the reactants, are on one side. The final products are on the other. To get from one side to the other, the molecules have to have enough energy to get all the way up and over that hill. If they collide but don't have enough energy, they just roll right back down. Nothing happens. Okay, so how many molecules in a given sample actually have enough energy to get over that hill? Well, for that, we look at something called the Maxwell-Boltzmann distribution. Don't worry about the name, just think of it as a census for molecular energy. At any temperature, you've got some slow-moving molecules, a lot of them with just average energy, and then you've got this tail on the right side of the curve. Those are your high-energy superstars, the really fast ones. Now, here's where it all connects. If we draw a vertical line on this graph to represent that activation energy hill we were talking about, you'll see something really important. Only the molecules to the right of that line, the ones in that superstar tail, actually have enough juice to react. And look how small that area is. It's a tiny, tiny fraction of all the molecules. This is why most collisions, even the ones with perfect aim, just don't work. Okay, so you may have heard this old rule of thumb in chemistry. Raise the temperature by just 10 degrees Celsius, and the reaction rate pretty much doubles. But hang on a second. Does that really make sense? A 10-degree bump makes things move a little bit faster. Sure, a few more collisions happen, but double the rate? That seems like way too big of a jump. So what's the real story? And here's the big reveal. When you raise the temperature, it does more than just make the average molecule a bit faster. What it really does is it stretches out and lifts that high-energy tail of the curve. So that small temperature bump causes a massive and disproportionate increase in the number of superstar molecules that can now clear that activation energy barrier. So it's not really about having slightly more collisions. It's about having way more effective collisions. And that right there is the secret power of temperature. Okay, enough theory. How do we actually see this stuff happen? Let's head into the lab, figuratively, and look at a classic, super visual experiment called the disappearing cross. The setup for this one is awesome because it's so simple. You take 2 totally clear liquids, mix them together, and a reaction starts that produces solid sulfur. This makes the solution get cloudy, kind of like dropping milk into water. So what you do is you put the flask on top of a piece of paper with an X drawn on it, and you start a stopwatch. When the solution gets so cloudy that you can't see the X anymore, you stop the clock. A quick way to estimate the rate is just to take 1 divided by that time. Now, this is a brilliant experiment for getting the basic idea because it's so visual, but it's not perfect. The biggest issue? It's subjective. What I call disappeared might be different from what you call disappeared. Plus, that 1/time thing is really just a rough approximation. It's good for comparing different runs, but it doesn't really tell you the whole story. So if we want to get more accurate, more detailed data, how do we do it? Well, we need a different experiment, one that lets us track the entire story of the reaction. And a great example is reacting magnesium metal with hydrochloric acid. With this one, you get a much clearer picture. You drop a strip of magnesium into some acid, and right away it starts fizzing like crazy. That fizzing is hydrogen gas being produced. And the cool part is, we can collect that gas. So instead of just waiting for one single moment, we can actually measure how much gas is being made over time, tracking the reaction's progress continuously. And when you plot that data, the volume of gas on the y-axis and time on the x-axis, you get this beautiful curve that literally tells you the reaction's life story. It starts out super steep, that's right at the beginning when the reaction is going full blast. Then, as the reactants start getting used up, the curve starts to level off, getting flatter and flatter, until finally it's completely horizontal. That's when the reaction is over. And here's the key takeaway from that graph. The steepness of the curve at any point, what mathematicians call the gradient or the slope, tells you the exact speed of the reaction at that moment. So if we want to know the initial rate, which is the fastest the reaction ever is, we just find the slope right at the start, at time equals 0. It's a way more accurate and powerful number than just timing how long it takes for a cross to disappear. All right, so this whole idea of getting precise rates from graphs is a perfect lead-in to our last section, the scientist's toolkit, where we'll compare some of these methods. So besides the ones we've looked at, chemists have some seriously clever tricks. Take the iodine clock reaction. This one is genius. It basically runs 2 reactions at once. The first one we're interested in, and a second, faster one that instantly cleans up the product of the first. But eventually, the cleanup chemical runs out, and bam! The solution instantly changes color from clear to dark blue. It's an incredibly precise way to measure that initial rate. So as you can see, it's all about trade-offs. The disappearing cross? Super simple, great for a quick look, but the endpoint is a bit subjective. The magnesium reaction? Awesome, you get the whole story of the reaction on a graph, but you might lose a little bit of gas right at the start. And the iodine clock? It's super accurate, but also way more complex to set up. There's no single best way. It's always about picking the right tool for what you're trying to find out. And of course, no matter what experiment you choose, none of them are perfect. You always have to think about errors. You've got random errors. Those are the unpredictable little things, like being a split second late on the stopwatch. You deal with those by doing lots of repeats and averaging them. Then you have systematic errors. These are the sneaky ones, like a leaky syringe that always loses gas, or a thermometer that's just plain wrong. These push all your data the same wrong way, and you can only fix them by improving your gear and your technique. So, let's tie it all together. What's the bottom line? The speed of any reaction, whether it's an explosion or slow rust, is all about one thing: how often you get effective collisions. And an effective collision needs the right orientation and, most importantly, enough energy to get over that activation hill. We can pull levers like concentration and temperature to control that frequency, and we use a whole toolkit of different experiments to measure exactly what's happening. So I'll leave you with this question. Now that you know the rules of the game, the things that control reaction speed, how would you use that knowledge? How could you speed up something useful, maybe an industrial process to make it cheaper or faster? And just as important, how could you slow down something you don't want, like the reactions that make food go bad? The science is the same. The application is up to you.